In this video, alright, we'll talk about slightly very similar things with regards to L7v2 and L7v3 and L7v1, alright, is to find the values of L, alright. Well, values of L, if you still remember your maybe I should rewrite. This value over here, alright, is equals, so L is equals to your K transpose, okay, where K is coming from the understanding of your Ackermanns, which is coming from your L7v3 and L7v2. Okay, you can watch this video first before coming back here. Alright, if you have watched this or you have some understandings, you can just continue, or you just want to know, just continue only. Alright, so same thing, we're going to introduce you with a simple system, simple calculation compared to the Ackermanns. So the Ackermanns one later on we'll deal with it in the next video, but I just want to introduce you with the simple concept. Alright, this is the transfer function over here. Alright, 2 over s squared plus 7s plus 12. Alright, then you have your poles as s plus 4 and s plus 3 if you were to factorize them up into here. Okay, this is your open loop transfer function. Alright, and your desired closed loop, which is C now, alright, closed loop, alright, we want it to be, alright, some value of zeros, alright, some arbitrary zeros lah, we don't care, but we only want it to be s plus 50, s plus 60, okay, so we want the poles over here to be shifted from here. So this thing over here, your open loop one, you want it to shift to your closed loop poles at here, okay, where your roots, it's minus 50 and minus 60, right, because if minus 50, then minus 50 plus 50, this one will be 0. So this is the roots, or anything makes the equation over here 0, or any of these things 0 is called the roots, if you still remember. Okay, and therefore one way is to derive the n in mind. Alright, I expand my s plus 50 times s plus 60, I have s squared plus 110s plus 3000. Okay, so my A observable S, which is our closed loop system, is this thing over here. Okay, so what is the K value then? The K value is simply taking s squared plus 110s plus 3000, okay, minus away s squared plus 7s plus 12. Okay, this thing over here is this line, while this thing over here is this one, right? So I'm taking our closed loop poles minus away our open loop poles. Okay, what I have, it's 110 minus 7 is 103, 3000 minus, because minus is minus 12 is what? 2988. Ta-da! What you can see. And s squared minus x squared is just simply 0 lah. So we're only taking 103,298. From here, as you can see, this is our K. Alright, but this is not as simple as it be if you were to go to Ackermann's stuff. Alright, but I'll just stop, I'll just tell you here first, alright, that K is equals to this thing. Alright, and we previously at the first part of the video we said that L is equals to K transpose. Alright, so therefore we can transpose this as 103 and 2988. Okay, and we can call this the K1, we can call this K2 and K1 better, okay, because of so that's why I suggest you to watch back these two videos, alright, these three lah, alright, if you haven't, that you forgot, just watch these three videos, alright, in the playlist. You should have a fair amount of what I'm talking, okay. Sorry, I should have said this as L, because now it's L now, where L is equals to your K transpose. Okay, this is your K2, this is your K1. If you transpose, this will become L2, L1. Okay, and therefore, right, what we can do now is to write this in terms of what is it? We'll live at this L first. Okay, because eventually if you have a L, alright, and then you can sub it into your the reason you may wonder, why do we find L? Alright, what is the end in mind to find L? Like L is something we find already, then what we're gonna use? Alright, if you still remember, your closed loop transfer function can be rewritten as this form. Remember? Correct? For the a minus kb, you can write in this form. Likewise, for our case is a minus lc, I can also write in this form. Okay, so I can represent my transfer function in terms of this thing. Okay, in fact, I also don't know whether I'm correct for this one, but this is some equations that can formulate a transfer function. Alright, with a multi-input, multi-output system, if you still remember. If you don't remember or don't find it very familiar, you can watch back L8v1, L8v2. Alright, these are talking about the stuffs that I'm talking now. Alright, therefore if you find a stuff, you rearrange, you should get a transfer function already. Okay? But in test, I don't think we're gonna use this thing anymore. We'll just somewhat stop here and that's it. Alright. And last but not least, okay, after we know that this is our K, this is our L, then we can sub in into our equation, right? A minus LC. Correct? And eventually we know that this must be 0 because this is our state error. If our state error is 0, this means that our model, if you still remember, our model will be equals to the real. Alright, so we have successfully modeled the real system. But anyway, this is 0, we will find the determinant of your A minus LC. Okay, so your L over here can sub in and then eventually it will help us shift our poles. If you remember, this is the open loop one, we shift to the closed loop one. Alright, eventually the closed loop one will output a certain responses that we want. Okay, which is pretty nice. Alright, and in order to check whether is our L correspond to this poles, okay, this is why my purpose over here in this last part is to prove to you that eigenvalue of A minus LC is minus 50 and minus 60. Okay, and in order to do this, I'll need to know what is my A and my C, right? These are all matrices. Okay, so that's why I change this transfer function, alright, into a state space. Alright, so this is my A, alright, this is my C. This is AX plus BU, this is CX. Okay, so my A over here, I'll not go into details because I've proved to you in L7v1. You can watch this video if you know how to change the state space. Okay, so once we have changed into state space, we will have this thing all over here, and this A and this C will be all along subit into here, right? So if I were to go MATLAB, because I'm lazy to calculate, so the eigenvalue of A minus LC, alright, is 60 minus 50. Okay, where my A is a matrix minus 7, 1, minus 12, 0. Alright, so my A is minus 7, 1, minus 12, 0, and my C is 1, 0, if you, yeah. So where is it? Yeah, my C is 1, 0, as you can see. So if you were to multiply and find the eigenvalue, you will get minus 60 and minus 50, which is the poles that we initially want. Ta-da! Okay, and this is the easier way to solve things. Alright, but however, they recommended Ackermann's method because I think if you're going to go to higher order, the calculation for K can be really tedious for this case. I don't know. So Ackermann's method will be better. But anyway, in the next video, we'll use the Ackermann's method again in order to prove that the value of L is equals to this thing over here. Alright, since you have already understand that what do we need to use for L, because our purpose of the L is to just sub it into the transfer function equation, and then you can know your overall transfer function straight away. Right, we have proved to you, I'll just mention to you just now, right? So yeah, therefore in the next video we'll use Ackermann's method, and that's it. Yeah.